Imagine a world where your secrets are protected, not by clever math, but by the very laws of physics. That's the promise of quantum security. But there's a catch. The biggest threat isn't hackers or supercomputers. It's distance itself. Let's start with the wall of distance. In today's quantum networks, information travels as single particles of light, photons, down optical fibers. These photons are incredibly fragile. As they travel, they get absorbed, scattered, and lose their quantum state. After just 100 to 200 kilometers, the signal fades into nothing. You can't just boost it like a regular internet signal. Why? Because of the no cloning theorem, a rule in quantum mechanics that says you can't make a perfect copy of an unknown quantum state. So classical repeaters, which simply amplify and resend data, are off the table. This leaves us with isolated quantum islands, unable to connect across continents. But what if we could leap over this wall? Enter the entanglement swap. Here's where things get wild. Instead of sending a fragile photon all the way from point A to point B, we break the journey into shorter hops. In each segment, we create pairs of entangled particles. Think of them as perfectly synchronized twins, no matter how far apart they are. At the junction between segments, a quantum repeater performs a Bell state measurement. In plain English, this is a special kind of joint measurement that doesn't reveal the actual information, but instead swaps the entanglement from the inner particles to the outer ones. The result? The two distant ends become entangled, even though their particles never met. It's like teleporting the connection itself, not the message. But there's a catch: the memory hold. For this entanglement swapping to work, we need quantum memories at each repeater node. These are materials or devices that can store the delicate quantum state long enough for the process to finish. And we're talking about holding on to these states at temperatures close to absolute zero, with timing precision down to trillionths of a second. If the memory fails, the whole chain collapses. This is one of the hardest engineering problems in physics today. So why does this matter? Because if we crack the code on quantum repeaters, we unlock a global quantum internet. That means unbreakable security, distributed quantum computing, and new tools for science and industry. The challenge is enormous, but so is the opportunity. If you're excited by the idea of building the backbone of tomorrow's internet, now's the time to get involved. The future of cybersecurity isn't just about faster algorithms, it's about rewriting the rules of what's possible.